So let's go over the bell work. Now we're looking into evaluating things, right? So far we've been synthesizing. I tell you what the elements are. You create, you write the formula, so you've been synthesizing. Now we're doing evaluation. So we're gonna look at these, 5 different compounds. You're gonna tell if they're possible. If they are not possible, you're gonna tell me what it should be, okay? So look at this first one. We have KS2. All right, is this possible, yes or no? Is KS2 possible, yes or no? You gotta talk to me. Is KS2 possible, yes or no? Okay, you say yes, let's see. What type of bond is this? It's an ionic bond. So do we need the charges? Yes, because ions, ionic. What is the oxidation for potassium?
1 plus 1.
Plus 1. What is the oxidation for sulfur?
-2.
What do we do with those numbers? We do what?
Swap and drop.
Swap and drop. Were these numbers swapped and dropped?
Yeah.
No, they were not. They were just dropped. If I have potassium with a plus and sulfur with a -2, they were not swapped and dropped. They were simply dropped. So is this possible?
No, man.
Is A possible?
No.
No. What should A be?
It should be K2.
It should be K2S, not KS2. You have to evaluate it. That's what evaluate means. Examine to see if it is actually possible. What is the name of K2S? Can't hear you. Potassium sulfide. Sulfate is a polyatomic ion. You change the ending to "ide," not "ate" or "ite." "Ide." Alright, next one. BeI2. Is it possible? Yes or no? And actually evaluate it this time. Don't just answer.
Yeah, it is.
Yes. Alright. How do you know? What type of bond is it making?
An ionic bond.
Ionic bond. What is the oxidation for beryllium?
+2.
Okay. And what is the oxidation for iodine?
-1.
Okay. So, was it swapped and dropped?
Yes, ma'am.
Yes. So what is the name of this
Beryllium iodide?
beryllium iodide? Alright, moving on. Next one. BaCl. Is that possible? Yes or no?
No.
What type of bond is that?
Ionic.
Ionic. What's the charge on barium?
2. +2.
Okay. What's the charge on fluorine?
-1.
-1. Were they swapped and dropped?
No, they weren't.
No, they weren't. So what should it be?
It should be Ba1Cl2.
Did we write ones?
I'm sorry.
You good? No. BaCl2 is what the formula should be. What is the name of this compound?
Beryllium chloride.
Not beryllium chloride.
Sorry, barium chloride.
Barium chloride. Barium chloride. Table 2. Make sure you're paying attention because y'all doing everything but. Alright. No, D. D. Is that possible? Yes or no?
Yeah.
Prove it.
Wait, no.
What type of bond is it?
It's an ionic bond.
Ionic bond. So lithium is what?
+1.
Alright. Iodine is what?
-1.
So what's the name of this?
Li.
What is the name of it?
Lithium.
Lithium iodide. Alright. Last one. Is it possible? Yes or no?
No.
No.
I don't even know what that is.
Alright.
Oh,
So what's the problem with that one?
The helium.
The helium. And helium is a what?
Noble gas.
Noble gas. What is helium's oxidation? 0. So is helium going to form a bond?
no, it's not.
No. So that is not possible, and there is no correct formula because helium will not bond with anything. Capiche? Alright. 2. Which diatomic molecules make single covalent bonds? Which diatomic molecule makes double covalent bonds? And which diatomic molecules make triple covalent bonds? So in order to answer this question, I must first know my what? Diatomic molecules. How many are there? 7.
It's a
And what are they?
bromine,
Bromine,
Oxygen.
oxygen, hydrogen, chlorine, iodine, fluorine, nitrogen. Your lovely Bro Clifton. Alright. So, of these 7, which ones would make single bonds to each other? It's diatomic, meaning there's 2 of them, and they're bonded together, right? Alright, so of these, which ones would be bonded together with a single bond? And how do you know? Let's take it one step at a time. Let's look at the first one, bromine. Remember, your nonmetals form bonds that equal to the number of electrons they need to complete their valence. Okay? How many electrons does bromine need to fill out its valence shell? 1. So how many bonds can bromine make? 1. So if a bromine is bonded to a bromine, what type of bond would that be? Single, double, or triple?
That's a single bond.
Single bond. So we know right here the single bond, my first one is bromine. Alright, let's go to oxygen. How many electrons does oxygen need to complete its octet? 2. So how many bonds will oxygen make? 2. So if oxygen is bonded to oxygen, what type of bond would they do that with? A single, a double, or a triple? Double. Gonna double bond. So that means oxygen goes here.
Okay.
Alright, let's look at hydrogen. How many bonds will hydrogen make?
1.
So where does hydrogen go? Single, double, or triple?
Single.
Single, okay. Let's look at chlorine. How many bonds can chlorine make? 1. So where does chlorine go? Single. What about iodine? Where will it go?
Same thing.
Single. What about fluorine? Where will it go?
Same thing.
Single. Alright, so what do I notice about the ones that make a single? They're either a halogen or hydrogen. Because my halogens can make how many bonds? 1. And hydrogen can make how many bonds? 1. So they can only make single bonds. Remember, that's why they can't be central atoms, because they can only make 1 bond. And to be a central atom, you have to be able to make at least 2. Because if I'm in the center, that means I have something at least on 2 different sides, right? At least. So I have to at least be able to make 2 bonds to be a central atom. So atoms in group 17, which are your halogens, and hydrogen can't be central. But they also can only make a single bond, because they can only make that 1 bond. Alright, what about nitrogen? How many more electrons does nitrogen need?
3.
So what type of bond will nitrogen make to nitrogen? Triple bond. They're going to share 3 pairs of electrons. So when it comes to my triple bond, that is only the nitrogen. Capiche? Capiche. Alright. What's the difference between a polar covalent and a non-polar covalent bond? What's the difference between a polar covalent and a non-polar covalent bond, just in general? What does covalent mean? What are they doing? Sharing. What are the 2 ways I can share? What are the 2 ways I can share something?
2 bonds.
No, okay, if I had a piece of cake, right, and I was going to share with one person, I can split it evenly, or I could not split it evenly, right? So I can share it equally. If I give them exactly half, I've shared equally. If I give them just a little bit off the fork, I still shared, but I did not share equally. Are you following? So when I'm sharing valence electrons, that distance between, from the electron to the nucleus of the atoms can either be about equal distance, because we have an equal pull or a near equal pull on the electron, or it can be closer to one atom than the other, which means there's an unequal difference. So covalent bonds can either be equal or unequal sharing of these valence electrons. So which one would be considered a polar covalent bond if it's sharing equally or unequally? Unequally. So this means this is unequal sharing. So that means if it is a non-polar covalent bond, then I have what?
Equal sharing.
Equal sharing. Never put the none with the un. None and un both mean not. We don't like double negatives. So if it's polar, the sharing is unequal. And if it's non-polar, the sharing is equal. Never put the none with the un. Following? All right. Now, this is just a general rule for how you know what's polar and non-polar. But now we're going to add some specifics. You should have at your table, there should be a chart. And on that chart, you should have your electronegativity values and your VSEPR chart. There should be at least two, one or two at each table so y'all can share. Y'all see those? If you are at a table where you don't see at least two and it's more than two people, grab one from a different table. Now, this is the number I need you to remember. 0.5 to 1.7. Okay, that's the range. 0.5 to 1.7. When I look at two atoms that are bonding together or that are going to react with each other, I look at their electronegativities and I find the difference. If the difference falls between 0.5 and 1.7, that is a polar covalent bond. If it's below 0.5, it's non-polar. If it's above 1.7, it's ionic. So I'm looking at the difference in electronegativities. So we're going to do one together, and then you're going to do these four, where you're going to tell me the actual value, and you're going to tell me whether or not that bond is ionic, polar covalent, or non-polar covalent. Now, we can pretty much look at a periodic table and predict whether or not something should be ionic, but we're going to prove it with the electronegativity values. Let's do barium and oxygen. Barium is a what? Metal or non-metal? Metal. Oxygen is a? What type of bond am I predicting? Ionic. Let's prove it. What is the electronegativity value for barium? Look on the table.
0.9.
0.9. What is the electronegativity value for oxygen? 3.5. What is the difference between 0.9 and 3.5? 2.6. So the difference is 2.6. So, is 2.6 an indicator of ionic, polar covalent, or non-polar covalent? Ionic. Because remember the range, the middle range, 0.5 to 1.7 is polar. Above 1.7, ionic. Below 0.5, non-polar. What's the range for polar? What's the range for polar?
0.5 to 1.7.
0.5 to 1.7. I want you to do sulfur and oxygen, cesium and sulfur, silver and fluorine, fluorine and fluorine. And I want the value, and I want to know if it is polar, non-polar, or ionic. Do it in. Ready?
I think so.
Yeah, this shouldn't take that long. Y'all got this. All right. What is it? What is the value for sulfur? 2.5. What's the value for oxygen? 3.5. What's the difference? 1.0. So what type of bond is that? Polar covalent. Because it falls between 0.5 and 1.7. The difference between 3.5 and 2.5 is 1. All right, what is cesium? 0.7. And sulfur is 2.5, which gives me a difference of 1.8. So that means it's what? Ionic, because 1.8 is above 1.7. Okay? Silver is what? 1.9. Fluorine is 4.0. That's a difference of 2.1. So that bond type would be ionic. What's the difference between fluorine and fluorine? 0. So what type of bond would that be? Non-polar. Okay? Y'all see how this works? Alright, so that's simple enough. Alright, does that answer your question you asked me at the beginning, Leela? Okay. Now, let's move back to evaluating the Lewis structure and using the valence shell electron pair repulsion to figure out the actual shape of a covalent compound. Okay? So, we're going to do this first one together, and then I want y'all to do the other 3. We'll do 2 together, and then y'all do the other 3. Alright, so let's talk about the actual process, just to remind you of what you should do. First, I need to check, is this an ionic or a covalent compound? Because we handle them differently. Is it ionic or covalent, and why?
Covalent because it's two non-metals.
Covalent because it's 2 nonmetals. Okay, I know this is a covalent compound. Before we move on, tell me if this is going to be polar or non-polar. Is it polar covalent or non-polar covalent? What are the bonds? What am I looking at? The bond between what and what? Nitrogen. What is nitrogen's electronegativity?
2.1.
What is nitrogen?
3.0.
I heard like so many different.
I'm sorry.
What is hydrogen?
2.1.
2.1. What's the difference? 0.9. So what type of bond is between nitrogen and hydrogen? Polar, covalent, because it falls in between the 0.5 to 1.7 range. All right, now, so that was just me making sure you knew how to do that. That's not a part of what you're supposed to be doing right now. But the first step in figuring out the shape of this molecule, now that I know it's covalent, do I care about its oxidation or do I care about its valence electrons?
The valence electrons.
Valence electrons. How many valence electrons do I have in this is ammonia, by the way. Ammonia is NH3. Ammonium, the polyatomic ion, is NH4+. Okay, so this is ammonia, which is NH3. All right, so how many valence electrons does it have?
It has
How many?
8.
It's 8, because nitrogen has how many? 5, plus my ones from hydrogen. How many valence electrons does hydrogen have? 1, and I have a total of 3 of those. So that gives me a total of 8 valence electrons. In this molecule, there are 8 valence electrons. All right, what's my next step? After I figure out how many valence electrons, I gotta find my what?
You got oxide.
Central atom first. What is my central atom between nitrogen and hydrogen?
Hydrogen.
No. What is it? Nitrogen. Can hydrogen ever be central?
No.
No. Remember, the rule is it's usually the least electronegative unless that is hydrogen or the halogens. Can they ever be central? No. So even though hydrogen is, what was I about to say? I lost my train of thought. Anyway, nitrogen is a central atom. We're going to, because my train, everything in my brain went out right then. Nitrogen is central. When I find my central atom, what do?
Your octet.
Give it an octet. Alright? What does octet mean, by the way?
8.
8. So I give it its 8. I gotta subtract that from my total. So So how many do I have left?
0.
None. I've used them all. Alright, now that I've placed those, what do I place next?
The hydrogens.
Place the hydrogens. Okay, I only had 3 of them. I placed them. I don't know why I put the one at the top. I hate putting it at the top. It doesn't matter. Like, this is a personal preference for me. Alright, now that I evaluate to see if everybody's happy. Needs a full valence shell. What is a full shell for hydrogen?
1.
What is a full valence shell for hydrogen?
2.
2. And for most other elements, the full valence shell is what? 8. So let's evaluate. Is hydrogen happy?
Yes.
Is this hydrogen happy?
Yes.
Is this hydrogen happy?
Yes.
Okay, let's check on my nitrogen. Is my nitrogen happy?
It looks pretty happy.
Yes, it's pretty happy. Now notice where I have overlap. What does that mean that's happening with these electrons?
They're bonding.
They're being shared. So I'm going to change those pairs to actual bonds. And we indicate the bonds with the lines. But I put my lone pair back. So that's one line. That's one line. That's one. Alright, so now I'm going to figure out the shape using the valence shell electron pair repulsion theory, right? Which atom am I looking at to figure out the shape of this molecule? The peripheral or the center?
The center.
The center, okay. And I'm looking at the electron density around the central atom. Anywhere there are electrons, whether they're bonding or not, is considered a domain. So how many domains are there around this nitrogen?
4.
There's 4 domains. And of those 4 domains, how many of them include lone pairs or non-bonding electrons?
1.
There's 1 lone pair. So what does that mean for the shape of this molecule? If there's 4 domains and 1 lone pair, then what is the shape? Trigonal pyramidal. Right, so that means the shape of this is trigonal pyramidal. It's a pyramid using 3 things. Trigonal pyramidal. The 3 things at the bottom of the pyramid would be the hydrogens. Alright, y'all following? Alright, so let's do not methane. Let's do carbon tetrabromide. Name it.
Carbon tetrabromide.
How do you know it's carbon tetrabromide?
There's 4.
There's 4 bromines, carbon. All right. Talk to me now. Cruising down the street, real slow. My railroad. Y'all know though. This way old. What I do?
Wait. So, carbon's 0.
Okay, yeah.
First you find the valences.
First I find the valences. Okay, how many does carbon have? 4 plus bromine, which has how many?
1, but
7 times 4, which gives me a total of how many? 32. So I have a total of 32 valence electrons. It needs 1 more. It has 7. Okay? Now what I do next?
You put carbon in the center.
Put the carbon in the center and do what with it?
Find its octet.
Give it an octet, okay? 4, 5, 6, 7, 8. Subtract the 8. How many do I have left?
24.
24. Alright, there's 24 valence electrons left. This is what I do. This is a trick for me. This does not mean you have to do it this way. You can place, after you place these other atoms, what am I placing around here first of all?
The bromines.
There's how many of them?
4.
4. So I'm going to go ahead and place those 4. When I have a lot of valence electrons, to keep from losing electrons in the count, I treat them as pairs, okay? If I have 24 valence electron, that is equivalent to how many pairs of electrons?
12.
There's 12 pairs. And now I have a total of how many elements I need to distribute them around?
4.
4. So if I take my 12 pairs and divide them by my 4 elements, that means that each element should get a total of 3 pairs. That helps me keep up with it when I'm doing the counting. So I'm gonna go here and I'm gonna go 1, 2, 3 pairs. 1, 2, 3 pairs. 1, 2, 3 pairs. 1, 2, 3 pairs. I've gotten rid of all of my electrons. You can sit and do the 24. You don't have to do that. That's just my personal way of keeping up with my valence electrons. Y'all following?
Yeah.
All right, now evaluate. Is everybody happy? Does everybody have an octet?
Mm-hmm.
Everybody has an octet. All right. What's the shape of carbon tetrabromide?
I don't know.
4 and 0.
So what's that 4 and 0? There's 4 domains with 0 lone pairs. What's the shape? Tetrahedral. Right. The shape would be tetrahedral. Capiche? All right. I want y'all to do. Name it. Name it.
Sulfur
Sulfur dihydride. Cool beans. So do sulfur dihydride. Do it on your boards. And then we'll talk about it.